Okay. Hi everyone, I'm Liang Ruichen from Singapore Management University. On behalf of my friend Cao Yuwei from the University of Illinois Chicago, the first author, I will share the research about multitask item attribute graph pre-training for strict code start item recommendation. In this work, we address the strict code start item recommendation, namely SCS recommendation task. The SCS settings is extremely difficult as the target SCS items are unseen during the training phase. Moreover, their historical ratings are available during the fine-tune. In other words, we only know the item contents of the SCS items, such as their titles, brands, price, categories, and descriptions. One feasible way to address the SCS recommended task is to transfer knowledge from the warm start items. As the warm start items, we have abundant information, including their contents, historical ratings, and review texts. Therefore, the existing SCS studies typically attempt to reconstruct the preference embeddings of the users and items from their content embeddings. In addition, recent recommended systems such as UnisRec and P5 adopts the pre-trained language models in their framework, since the language model naturally addresses unseen item contents, so these recommended systems can capable of the according SCS items. However, this method merely explores the available data source in course-grade manner. Especially the existing studies ignore both the review texts and the item correlations contained in the user rating sequences, such as the UnisRec just simplify concatenates the item contents and truncates the item information due to the input length limitations of the pre-trained language models. And the P5, they just treat the item ID sequence as a natural language sequences. So such coarse-grained manners lose useful information of the item content and introduce noise. So in this work, we leverage available information in fine-grained manner. Especially we study how to effectively use the item attributes to associate the SCS items with the warm items. And we observed that although the new items are ever emerging, their attributes are relevant and stable. So based on this observation, we construct an item attribute bipartite graph and transfer knowledge from various data sources into this graph via pre-training. So during the prediction, we can then insert the SS items with the new attributes into the pre-trained item attribute graph and propagate the neighborhood embeddings. So this gives us the informative embeddings for the SCS items. So this lower figure shows an example. So on the left-hand side, we pre-train an item embeddings that contains restaurant A and B and their attributes. So when we have a new restaurant C, we can insert it along with the new attributes family-owned into the graph. And by propagating and fusing the embeddings of restaurant C's neighborhoods, including the Italy, pizza, and family-owned, we can get the embedding for the restaurant C for the recommendation. So to achieve the above goal, there are 3 questions to be answered. The first is how to model fine-grained item attribute correlations. And the second is how to transfer knowledge from various data sources. And the third is how to simultaneously incorporate all knowledge. For the first question about modeling fine-grained item attribute graph, attribute correlations, we extract the attribute of item from their contents and insert the attributes and the item into an item attribute bipartite graph as shown in the lower figure. Particularly, the upper figure shows how we can extract the attributes. So the category information such as the brand are directly inserted into the graph. And for the long and noisy fields such as descriptions, we carefully pre-process them and extract the non-phrases to serve as attributes. For example, for the sampled item, we can extract attributes such as garden supplies and holiday decorations, which is better describes the item compared to the raw descriptions field. So for the second question about transferring knowledge from various data sources, specifically, we design different submodules to embed these different type of data sources. First, based on the constructed item attribute graph, we transfer knowledge from the item content field. We embed the item attribute into the graph by capturing the natural language schematics of the item and the item as well as the high-order structure information, which contains the correlation information. So as shown in the figure, the embedding submodule contains pre-trained language models that can extract the natural language schematics from the items and the attributes nodes. And then an interpreter, which is an MLP-based interpreter, can map the node embeddings into a lower dimensional space. And then finally, a graph neural network is used to exchange the information between neighboring nodes. And to transfer knowledge from the user purchase sequences, we leverage a transformer-based sequential module, which is similar to the BERT for Rec, to extract the content item correlations. Such a design choice is based on the observation that the sequential module have the good performance in modeling user purchase sequence. As shown in the figure in the middle, the submodule takes in the purchase sequence as input, which is a sequence of items. And some of the item will be masked out, and then the sequential submodule need learn to reconstruct the item embedding from the remaining item embeddings. Therefore, the embedding from this submodule will contain the correlated items information. Because the review texts contain useful information, they reflect users' subjective perception of the users of the item attributes, so they can serve as valuable supplements to the objective item content. So we also seek to transfer knowledge from the review texts. As shown in the right figure, similar to how we model the item attribute correlation, we also construct an item attribute bipetitle graph and embed the graph with the pre-trained language models, the MLP-based interpreter, and the graph neural networks. So the item embedding learned from this submodule contains item review correlations. So due to the high volume and the complexity of the raw review texts, using them directly can be ineffective. So inspired by the previous study about phrase-level sentiment analysis, we extract the phrases with the sentiments and use them to represent the reviews. For example, as shown in the bottom figure, we can extract good container from the raw text about the container is extremely durable. So such a method will be more effective in describing users' opinions. And for the third question about simultaneously incorporating our knowledge learned from the submodules, we shared a set of item embeddings between them and co-train them in a multitask manner. So this process is shown by two blue arrows pointing from the first submodule to the second and the third submodule in the figure. However, we observe that if we adopt the commonly used loss, such as BPR loss, info NCE loss, and cross entropy loss for each submodules, the knowledge cannot be fused effectively. So therefore, to address this challenge, we design a multitask alignment and uniformity loss, which can effectively fuse the knowledge across the different tasks. So for each task, we adopt an alignment term and a uniform term. The alignment term of the three tasks, as shown on the bottom, is used to align the shared item embedding with the embeddings of the attributes, the correlated items, and the review term, respectively. Particularly, the distance between this embedding will be minimized, and so that the knowledge can be fused. And the uniformity terms, on the other hand, is introduced as a regularization by differentiating items and attributes, so that all the embedding can not be just collapsed into one point. Particularly take the uniformity terms of the first submodule as example. It contains two terms. The first term maps all item embeddings so that after mapping, all the item embedding can be distributed on a unit hypersphere. And so this part can push the item embeddings to be as far away from each other as possible. And similarly, the second term is push the attribute embeddings far away from each other. So eventually, the overall loss is the weighted sum of all the tasks. And we evaluate our method. We conduct experiments on Yelp, Amazon Home, and Amazon Sports. We carefully process this dataset to guarantee the SCS settings. And we also compared our proposed method with content-based models such as BERT and the SCS recommender system such as DropNet, and also with the pre-trained models such as UnisRec and P5. So the main observation is that our proposed method, namely CodeGPT, can outperform the baseline by large margins. For example, it can outperform the best baseline, the UnisRec recommender system, by over 16% in Yelp dataset measured by NEC JAD5. And we further compared to the UnisRec PD, which is the pre-trained model over 75 times more data compared to our method. But our proposed CodeGPT can also outperform this pre-trained model on two datasets. And for the ablation study, as shown in the figure 1 and figure 2, so all the three submodules can contribute to the good performance of our proposed method. So we also observed that our proposed multitask alignment and uniformity loss performs notably better than adopting the conventional loss for each task. As shown in the figure C and figure D, when we adopt the conventional loss for each task, the loss during the training phase will shake heavily. And when we adopt the proposed loss, the loss will reduce smoothly. And to conclusion, first, fine-grained modeling of item correlations such as adopted by our model works better than the coarse-grained modeling. Second, various data sources, including the item contents, purchase sequences, and review texts, contain knowledge that can help SCS item recommendation task. Also, to model the data sources, we should consider the natural form of the data sources, such as the sequence, the graph, the natural language sequence, and we should choose the model appropriate architecture. And finally, the proposed multitask alignment and uniformity loss can effectively incorporate knowledge learned from the various data sources and submodules. So that's all. Any questions are welcome. Although I'm not the author of this paper, but I'm welcome all the questions. And you can also leave the question on the live hub. So you will give more details.
All right, thank you. Let's thank the speaker. I did not see any questions on Slido. If you have questions in the room, the microphone is here. I do have some questions, but feel free, like if you don't know the answer, that's okay. So one question I have is about the sequential aspect.
Yeah, sequential aspect.
So it models purchase sequences,
Yes.
but it did not seem that that's. It seems like the model is more general than that, and if you didn't have sequence data, it might still work just fine. So I was wondering if you studied, in terms of like ablation, whether just having purchases is enough, or if the sequence data is actually essential.
Okay, thanks for the question. So in this paper, we modeling the sequential models, sequential information. Such we incorporate the user purchase sequences in this submodule. We designed a transformer-based method, which is similar to the but for rec. So it will take the user purchase sequence as the input, and the embeddings from the input is used from the first submodule, and in the modeling process, some of the input sequence will be masked, and then the model will learn to reconstruct the embeddings. So we can make this module to exchange the knowledge between different items and get the fused item for the recommendation.
So you think the sequence is helpful?
Yeah, we just use the sequences.
Any other questions? All right, I have one more. And this also kind of pertains to the, you put a lot of different technologies together in this. And one, there were some interesting natural language processing parts to do, extract noun phrases, extract sentiment, and these kinds of things.
Yes.
And so my question is kind of how sensitive the results are to those natural language processing pieces, because of course that's where you're getting the data for cold start, the attribute matching. So did you look at different methods for handling that data, for looking at just the data? What happens if we just take the raw embeddings of the reviews, for example?
So in this work, we just use the existing techniques to extract the sentiment phrases. So it's just a part of our proposed method. So with the development of the sentiment analysis, we can incorporate them into our proposed method to get more precise prediction. So this is not the key point of our proposed method. We just use it to extract the sentiment phrases. So the developer of this technique will be helpful for our task.
Okay, thanks. Are there any Slido questions? No. Okay. I don't see any questions here, so let's thank the speaker once more.
Thank you.
Thank you. Thank you for doing it.